In the last lecture, we discussed the basic issues about fiber optic communication. We saw the history of communication, that as the time progressed, the frequency of carrier increased in a continued fashion over last 1 century, and around middle of the century the carrier frequencies were in the range of microwave or millimeter waves. In the search of larger bandwidth, then the optical window was explored, and then we looked for the media which were available for transmitting light over long distances, and also we asked the questions whether optical sources were available for carrying information on this medium over long distance. Then we also saw a comparison between different transmission media like the coaxial cable or the twisted pair or satellite communication, and then we found that the satellite communication and fiber optic communication are complementary in nature. So, whatever we can achieve with satellite communication cannot be achieved with optical communication and vice versa. So, then we conclude that these two technologies, the optical fiber communication technology and satellite communication technology, have to coexist because they have a complementary nature. We also saw that initially when the testing on material glass was made for the attenuation, it was found that after first purification, the loss in glass was about 20 dB per kilometer. And we argued at that time that although this loss was not very low, this loss was very comparable to the alternatives which were available that time, that means the coaxial cables. However, since then the technology has consistently worked on purifying the glass, and as a result the loss in glass has come down significantly. So, let us look at the history of attenuation for glass over last 50 years. So, initially when the glass was tested, this was sometime in 1970, you had a profile of loss as a function of wavelength, which was something like that. So, there was a low attenuation region somewhere around 800 nanometer or 0.8 micron wavelength, and when this testing was going on, at the same time, as we mentioned, the lasers were invented, and the semiconducting material which was most studied for emission of light was gallium arsenide, and gallium arsenide, we will see later in this course, is intrinsically capable of emitting a wavelength which is around 0.8 microns. So, in fact, this was a great combination that we had the loss profile which had a minimum around 800 nanometer wavelength, and also we had the sources available which were based on gallium arsenide. They were capable of emitting light at 800 nanometer. So, this combination of gallium arsenide based devices and the low loss region of glass made the optical communication possible around 1970. This is the region now we call as the first window of optical communication. So, in fact, when the optical communication started, most of the communication was set up in this window which is around 800 nanometer or 0.8 micron. As the time progressed, then the glass was purified further and further, and then the loss profile now is modified to something like this. So, first thing to note here is there is no window which has a minimum around 800 nanometer now. So, the window of low loss has now is around either 1300 nanometer or around 1550 nanometer. There is some region here where the attenuation is very large. So, one can say that by the time we came to about 1980s, the loss profile was something like this. That means there were two windows for operation. One was around 1300 nanometer, one was around 1550 nanometer. As soon as this was realized, and in this time Even the material technology had improved significantly. So, you could identify the materials which could give emission of light in any window of this range. So, we could develop the sources which could emit light around 1300 nanometer or which could emit light around 1550 nanometer. So, immediately the optical transmission was shifted from 800 nanometer to 1300 nanometer. Later on we will see that this 1300 nanometer is a very special window, because not only in this window the loss is low, but also this window can support high data rates. That means this window has a very large bandwidth. Well, the 1550 nanometer window has a loss which is little smaller compared to the loss at 1300 nanometer. If I give the number, here the loss will be about 0.2 dB per kilometer at 1550 nanometer. At 1300 nanometer, the loss is typically of the order of about 0.4 dB per kilometer, and at 800 nanometer, the loss is typically of the order of about 3 dB per kilometer or 4 dB per kilometer. So, what we then find is that shifting the operation wavelength from 800 nanometer to 1300 nanometer, we had significant improvement in the loss performance. And that is the reason, as I mentioned, the window of operation was shifted in 80s from 800 nanometer to 1300 nanometer. Later on, even the difference of 0.2 dB per kilometer between 1300 nanometer and 1550 nanometer was becoming significant, because the distances were becoming very large. So, later on the window was shifted from 1300 nanometer to 1550 nanometer, and today most of the transmission takes place in the window of 1550 nanometer. So, the 1300 nanometer window, which was dominant in 80s and maybe in 90s, this we refer to as the second window of operation, and the 1550 nanometer window is we call as the third window of operation. So, if you look at the optical communication today, most of the optical communication takes place around 1550 nanometer, and later on we will see some other advantages of this window, because we could have now the optical amplification possible in 1550 nanometer window. So, when we have a very long distance communication, you can even have periodic amplifiers installed which can amplify the signal without converting into the electronics. So, these are certain advantages which essentially made this window of 1550 nanometer very interesting and applicable window, and that is the reason most of the modern communication takes place in this window of 1550 nanometer. With this, now let us see some in general what are the now advantages of optical communication. So, the two advantages which you have highlighted are the ultra high bandwidth. So, as I mentioned, if I look at the loss profile here, and if I look at the bandwidth, which is typically of the order of about 50-60 nanometer here, or similar type 50-60 nanometer here, you have a bandwidth of typically hundreds of gigahertz, which is available in this window, which is available in this window. So, just if I define the bandwidth on the basis of low loss performance, then we have got a huge window around 1300 nanometer, and we have got a huge bandwidth around 1550 nanometer. So, this is one of the major advantage of optical communication. This has a ultra high bandwidth of the order of about terahertz. Also, as we saw that if I go to the wavelength, which is of the order of 1300 nanometer or 1550 nanometer, then the loss is as low as 0.2 dB per kilometer. So, as we mentioned in the beginning, for good high quality communication, you require two things. You require high signal to noise ratio or low loss in the system, and a large bandwidth. And optical communication gives you essentially both. It gives you a very large bandwidth, it also has a very low loss. In fact, if you compare this loss of 0.2 dB per kilometer with all other alternatives, you will see there is no medium today which can compete with such a small loss. The medium like coaxial cable or any other structure which has a loss which is much higher, and of course, this bandwidth also is very limited. So, then we have a very strong case for now optical communication, because it supports a very high bandwidth with a very low loss. Well, with this, then we can go to the further advantages of optical communication, and next is the low EMI. So, you have very low electromagnetic interference when you transmit the signal in optical form. One can ask a very basic question at this stage, that light is also an electromagnetic wave. So, what is so special about this? When we increase the frequency from kilohertz to megahertz to gigahertz, as the frequency increased, there was more and more electromagnetic interference. So, what has suddenly changed when we increase the frequency still further from microwave frequencies to the optical frequencies, which is about 3 orders of magnitude higher. So, one can ask, if I have a coupling between different components, what scale the coupling takes place between the electromagnetic fields, or what distances we have the electromagnetic interference. So, typically you see that the electromagnetic interference is strong if you have distances which are comparable to wavelength. So, when we operate at microwave frequencies, the wavelengths are typically of the order of few tens of centimeters. So, a typical electronic circuit, there is a coupling between different components, because the separation between the components is comparable to the wavelength. When you go to the frequencies like optical frequencies, where the wavelength now has become typically of the order of 1 micrometer, you will see electromagnetic interference if you bring the components within a distance of 1 micron. So, if you have distances which are much larger compared to 1 micron, then there is no coupling between these components, and that is what precisely we are talking about, that this one gives you a very high EMI performance, because the distances which we talk are much larger compared to the wavelength of operation at optical frequencies. The next advantage which we have is security of transmission. That is, once the signal is put in a medium like optical fiber, the signal cannot be tapped from outside. This was not true if I had a medium like, let us say, a twisted pair. If the twisted pair is there, the most of the electromagnetic fields are outside. So, just without physically touching these cables, we can always put some coupling device which can couple the fields of the twisted pair, and these fields can now give you the information which is flowing on the twisted pair. Since no light leaks from the optical fiber, at least in ideal condition, then there is no possibility of tapping the data or information which is flowing inside the optical fiber. So, it gives you a very high security of transmission. Later on we will see, well, that this statement has to be taken with little caution, because this is a very ideal situation. As soon as you go to the practical systems where the fiber is deformed and so on, there is always a leakage of information which can be tapped. The next advantage of optical communication is low manufacturing cost. So, here if you look at the cost is primarily in the technology, in the material processing. The basic material, which is glass, is practically free. It is silica, and silica is very abundant in nature. So, if you ask where the cost is, the material cost is practically zero. The cost is in technology for purifying this glass and then making this glass in the form of optical fiber. So, in contrary to other media like coaxial cable, where the material used is like copper, which is a very expensive material, the most of the cost goes into material, whereas in optical fiber, the most of the cost is only in technology, and the material cost is practically zero. Also, you should see this statement in a little different way. If we compare the cost of optical fiber with a coaxial cable per kilometer, maybe the cost will be very comparable. But if we ask, what is the cost per voice channel flowing on optical fiber? and the cost per voice channel flowing on a coaxial cable. Since the optical fiber can carry the voice channels which could be 1000 times more than a coaxial cable, the cost per voice channel will be 1,000th of the cost of the coaxial cable. So, even if the cost per kilometer of these two are comparable, the cost per voice channel would be much smaller for the optical fiber. So, that is where we have a significant advantage there. Then of course, as we will see here later in this course, that the optical fiber is a very thin glass rod. So, it is very low weight and it is not very voluminous. So, in those situations where the volume or weight is a constraint, like space-bound devices and so on, the optical fibers could be much more advantageous than any of the metallic cables. Only disadvantage, if at all, we want to point out for optical communication is that it is point-to-point communication. As we saw, satellite communication is a broadcasting medium. You can transmit the information from one point to multi-point, whereas in case of optical communication, since it is a wired communication, the point information can go only from one point to another point. However, at least in urban areas where you have now a good network of optical fiber, practically every house in the city can be reached by optical fiber. So, though the technology intrinsically is a point-to-point technology, you can use it like a broadcasting thing because the fiber is practically reaching to every home, at least inside the cities. So, then we see that the optical communication has many more advantages compared to any other mode of communication. Not only large bandwidth and low loss, but it gives you many other features also which are very attractive. That is what precisely is the reason why optical communication technology grew so rapidly in last 30 to 40 years. In fact, every 10 years there has been a completely revolutionary change in the optical communication technology. So, the technology which was in 70s was obsolete by 80s, the technology which was in 80 became obsolete in 90s, and the same is true even from 90s to the beginning of this century. So, optical communication has grown very, very rapidly, and of course, the credit goes to the material science technology which gave high quality materials for making fibers and optical sources. Also, it has been because of the improvement in the communication technology. So, today if you look at the networks are using the optical fiber as the backbone. Large number of wavelengths are transmitted, what are called wavelength division multiplexing systems, and the overall capacity of this optical communication system has been very, very large. With this, then now let us get into the first topic of the optical communication, and that is the optical fibers. However, before we get into the optical fibers, let us first revise some of the basic concepts of light. We know the light is an electromagnetic radiation. We also know that in high school we have studied light as rays. So, we could establish the laws like Snell's law, laws of reflection, refraction, treating light as rays. And then we also know that the light could be treated like photons. So, in fact, you have to deal with light depending upon the context in any of these three models. So, what we do in this course, first we establish some of the basic things about the light in terms of ray model. So, first we treat light as a ray. Then when we find that this model, the ray model of light is inadequate for explaining some phenomena, then we depart to the higher level of model, which is the wave model, where the light is electromagnetic wave. And in those situations where we find the wave model cannot explain the phenomena like interaction of light with matter, then we go to the model which is the quantum model, where light will be treated like a photon. So, in this course essentially we start with a ray model, then we will go to the wave model, and then finally we will go to the quantum model of light. Let us now ask that if a light source is given to us, what way the light source can be characterized, and especially from the communication point of view, what are its implications. So, firstly, as all of us know, that a light source can be characterized by what is called the intensity of light. Now, the intensity of light is the power per unit solid angle. So, for a given power, if the light is confined to a very narrow beam where the solid angle is very small, then the source will appear brighter. So, this is one of the parameters which essentially tells me how focused the light is. So, for a given power, if the light goes into a very wide angle like a normal bulb, then it will not appear as bright as the laser would appear, even the power of the laser is very small, but that power comes in a very narrow cone. So, laser light appears much brighter compared to the light which we get from a simple tube light. So, that is one of the characteristic parameter of light. The second parameter which is of light is the wavelength, or in the common terminology, that is the color of the light. However, as we have seen earlier, that the low loss window for optical communication is 1300 nanometer or 1550 nanometer. The visible range of light is somewhere here, which is from 400 nanometer to 700 nanometer. So, that means the glass which seems to be so transparent to the human eye, it is not really fully transparent at the optical visible wavelengths. In fact, it is much more transparent in the wavelengths which are lying in the infrared region, which are in 1300 nanometer or 1550 nanometer. So, since the operation is not now confined to the visible range of light, the color does not have any sense, but still we can use the same notion of color to characterize the light. So, we say that the second parameter which is important for the optical communication is the color of the light or the wavelength, and this quantity we can say is, let us say, some lambda. Depending upon the loss performance, we can choose lambda either in 1300 nanometer or 1550 nanometer. So, the choice of wavelength has a direct bearing on the loss performance of your optical communication system. The second parameter which we have now is which is related to the spectrum of light, is what is called the spectral width. Let me denote this quantity as, let us say, delta lambda. So, it is the wavelength range over which the emission takes place. So, we can say that the spectral width is something like a purity of the color. So, the wavelength is representing a color, then the spectral width represents purity of the color. So, if I have a very wide spectral range, let us say in visible range it goes from the blue to red, then I will get a light which will look like white light. If I reduce the bandwidth to a smaller region, let us say around red, then I will get a very sharp red color. If I put a wavelength around yellow, I will get a sharp yellow color. If I move the wavelength around blue, I will get a sharp blue color. So, reducing the wavelength essentially increases the purity of the color. So, we find now that the spectral width, which in terms of the normal human vision is the purity of the color, is important parameter, because later on we will see that this is directly related to the data rate which you can transmit. Smaller the value of delta lambda, higher will be the bandwidth of the communication system, or higher the data rate which you can transmit on the optical fiber. So, the choice of wavelength has a bearing on the signal to noise ratio or loss, and the purity of the color or the spectral width has a direct bearing on the bandwidth of your optical system. So, these two parameters are extremely important parameters for the optical communication. Of course, these three parameters, the intensity, the wavelength and the spectral width of the light source, treat light as an energy source. nowhere the wave nature of light comes into picture. So, you have an energy source which is giving you certain power, you find out or what angular zone the power is confined, which is related to intensity, what color the light has, it gives you the wavelength, and what is the purity of the color, it gives you the spectral width. However, when we talk about the propagation of light inside the optical fiber, the light cannot be simply treated like a energy source. It has to be treated like an electromagnetic wave. And if you use the electromagnetic wave, then at least if the medium is very large, we treat the light as a transverse electromagnetic wave. What that means is that if I consider a light energy source, and let us say light is moving something in this direction, the light is transverse electromagnetic, that means it has electric and magnetic fields like that. So, this is the electric field for the light, this is the magnetic field for the light, and this is the direction of light. So, wave propagates in this direction. So, the electric field, the magnetic field and the direction of light or the wave, they are perpendicular to each other, and if I put my fingers going from E to H, then my thumb points in this direction, which is the wave direction. So, in a medium which is having a size much larger compared to the wavelength of the light can be treated like a transverse electromagnetic wave, and then the E and H are also related through the medium parameters. So, you have this quantity E by H magnitude, that is equal to a quantity called eta, which is intrinsic impedance of the medium, and which is given by the square root of permeability of the medium divided by the permittivity of the medium. So, in fact, the electric and magnetic fields are related through the medium parameters. They are perpendicular to each other and are perpendicular to direction of the wave propagation. So, H is completely dependent on the electric field. So, if I treat the light as a transverse electromagnetic wave, then I at least should observe the behavior of E as a function of time. Once I know the behavior of E, H I can always find out, because H is always perpendicular to E, and E by H, that ratio is given by the medium parameters. This behavior of light as a function of time, that means the way the electric field behaves as a function of time, that is what is called the polarization of light. And this is one of the very important parameters of any electromagnetic wave. So, if I now treat the light as transverse electromagnetic wave, then the electric field vector treated like an arrow, the tip of this vector will draw as a function of time different shapes, and that shape is what is called the state of polarization. So, in fact, the polarization is a parameter which captures the vector nature of light. All these quantities, the intensity, the wavelength and the spectral width, they treat light as a scalar quantity, because it treats only light as an energy source. Whereas, this is the quantity polarization which says that the light is made of electric and magnetic fields, and that is why there is some vector nature associated with that. So, in general, if I ask what kind of shapes are drawn by the light, then you can get in general a shape which will be elliptical shape. So, if I look at the tip of the electric field vector as a function of time, the electric field vector will draw a shape which will something like that, and then we call this behavior is the polarization, and since the shape is elliptical, we say that this light is elliptically polarized. So, in general, one can say that a light is elliptically polarized. In some special cases, the ellipse can degenerate either into a straight line or into a circle. So, if the ellipse is compressed, it becomes a line, and then I call this polarization a linear polarization. If the ellipse is stretched so that the major axis and minor axis become equal, then this becomes a circle, and then I call that polarization as a circular polarization. So, a general state of polarization which is elliptical can degenerate into either a linear polarization or into a circular polarization. So, in general, then we can say a transverse electromagnetic light has three states of polarization: linear polarization, circular polarization, and elliptical polarization. Also, if the light does not have a systematic behavior like this, which would happen if I have a light source has a very large bandwidth, then the electric field vector as a function of time orients randomly, its amplitude varies randomly, and then we call that state of polarization as a random polarization. So, typically the lights which are so called incoherent light, they do not have any definite state of polarization, and we can call that as a randomly polarized light. So, this is the parameter which is the important parameter for wave propagation, because this parameter essentially describes the vector nature of light. With this now, let us come to the simplest possible description of light, what is called the rays. So, there are two possibilities. One is, let us say I have a light source here, and this light source essentially throws the energy out in the optical form. The energy propagates radially away from this source. But what essentially we have is a wave which is travelling away from this in the form of the spherical shells. So, essentially these lines which you are drawing here, what we call rays, are only the fictitious lines. What actually is travelling is this, what is called the phase front or the constant phase surfaces. So, if I look at these constant phase fronts here, they are the one which are moving radially outwards, and if I draw the lines perpendicular to these phase fronts at every point, then they give me a representation of light in the form of rays. So, in fact, there is nothing like a ray. What we have here is a phase front which is moving, and if I get a collection of these phase fronts and draw these lines which are perpendicular to them, then they give us what are called the light rays. So, if you are having a source located at a finite distance, then the wave essentially would be what is called a spherical wave, because the phase fronts are like spheres. Let us say if I push this source very far away and I see from a very long distance, practically the phase front from a very long distance will almost look locally like a plane, and then the phase front will look almost like a plane here. That means, if I look at a source from a very far away distance, practically the phase fronts have become planes and they are parallel to each other. Then the lines which are perpendicular to this, which we call rays, are these parallel lines. So, this wave then we can call as the plane waves. So, whenever we have a source at a finite distance, the light which is emitted by that is of spherical nature, whereas if the source was very far away, then we can say practically that the light has become like a plane wave. And then in this case, essentially if you draw a ray like this, the ray essentially means that there are phase front which are perpendicular to that, which are travelling, and this line is just a representation of those phase fronts. So, later on when we talk about propagation of light inside optical fiber, first we will try to explain certain phenomena with the help of simply rays, and then we will slowly put the phase front behind them and then ask a question whether our understanding was correct or not, and we will refine our observation. The second basics of light is that if I consider the light as an electromagnetic wave, then any wave phenomena can be defined by a function which is like this. So, a wave function psi, which is a combination of space and time, has an amplitude A and has a phase function which is omega t minus beta x. There should be j here, but this is a phase function. So, now the phase of this quantity psi x of t is a combination of omega t, which is the time, and the space, which is beta x. So, if I say that I freeze time, that means, if I make x equal to constant minus beta x is a constant quantity, then this quantity psi x comma t, it has an amplitude a and it varies e to the power j omega t. So, it has a sinusoidal variation as a function of time, and omega is the angular frequency. If I freeze time, that means, if I instantaneously look at this function in space, this quantity is constant now. Again, I have a sinusoidal variation with e to the power minus j beta x in space. So, we have this function, wave function, which is a combination of time and space. The function varies sinusoidally in time at a given location in space. It varies sinusoidally in space at a given instant of time, and the two together essentially constitute what is called the wave phenomena. So, since this quantity here beta x represents phase in space, we call this quantity beta as the phase constant. Omega, as we all know, is what is called the angular frequency of the wave. It has units radians per second. And here we have this quantity beta, which we call as the phase constant. And since beta into x gives you phase, the beta is the phase divided by distance. So, it has a unit which is radian per meter. Now, if I look at the phase fronts here, if I consider the two phase fronts which are having the same phase, that means the difference between them is 2 pi. By definition, any 2 points on the wave which are having same phase is called the wavelength. That means, if I consider the 2 points separated by a distance which is 2 pi, then that distance we call as the wavelength. So, that means, beta into distance lambda, which is the wavelength, that should be equal to 2 pi. So, essentially the phase constant beta which we have here is by definition is 2 pi divided by lambda. So, in any propagation of light, if we know lambda, then we can find out what is the phase constant beta, and if we know the phase constant beta, we can find out the corresponding wavelength lambda. One may wonder at this point that once I know the frequency of the light, then I can find out the value of lambda, and from this relation I can find out the value of beta. So, what is so special about it? But what one should note at this point is that the lambda is not always the velocity of light divided by frequency, because velocity of light is a medium dependent property. If you go from vacuum to another material, the velocity of light changes. If you go within the same material, but if you make the medium bound, the velocity of light changes. That means, this quantity velocity of light is medium dependent, is structure dependent. So, once you know the frequency of light, you can either find out this constant phase constant beta. Once you know the value of beta, then you can find out from this relation what is the value of lambda, and then this lambda multiplied by the frequency, that gives you essentially velocity of light. So, we will use this concept more often as we progress later in this course. Now, if you consider the light as an electromagnetic wave, transverse electromagnetic wave, then we have an important parameter defined, what is called the refractive index of the medium. And refractive index of the medium is defined as the velocity of light in vacuum divided by the velocity of light in that medium. So, we have this important quantity here, what is called the refractive index, and let us denote that by n, that is equal to the velocity of light in vacuum C divided by the velocity of light in that medium V. Since for most of the dielectric media which we will be discussing here, the refractive index is greater than 1, the velocity of light always reduces when the light goes from vacuum to the medium. So, light in fact travels fastest in the vacuum, and in any other medium it slows down. If you take a material like glass, the refractive index of glass is approximately 1.5. If you take refractive index of water, it is about 1.33. So, this parameter is essentially telling you by what factor the speed of light reduces when it enters that medium. Later on we will see there is something called the effective refractive index. So, we have a quantity which is effective refractive index, N effective, which is again defined as C divided by the velocity of the light. But now this velocity of light need not be only in a medium which could be of unbound nature. This velocity now is a structure which could be like an optical fiber structure or a bound structure. And we will see that the velocity, since it is structure dependent, as the size of your medium changes, this quantity velocity will change. So, keeping the medium same, just by changing the size of the medium, you will have a change in the velocity of light, and as a result by this ratio will change. So, we say effectively the refractive index of that guiding structure would change. So, later on we will see that this concept of effective refractive index will be used more frequently in defining the propagation of light inside the optical fiber. As we mentioned earlier, normally when we talk about light, we do not talk about frequencies, but we describe the light in terms of wavelength, just for historical reason, because earlier the light was characterized by its wavelength in terms of angstroms. So, here also we maintain that tradition, and that is the reason, as you saw, that we define the windows of operation not in terms of frequency, but we define these windows in terms of wavelengths. So, we had these three wavelengths which were 800 nanometer, then we had a window which is 1300 nanometer, and then we had a window which is 1550 nanometer. Nanometer is 10 to the power minus 9 meters. So, essentially 1 nanometer is equal to 10 to the power 9 meters, and wavelength is nothing but the velocity of light divided by the frequency of the light. Now, to define the spectral width of the source, we require the parameter what is called delta lambda, and delta lambda you can write as minus V upon f square into delta f. So, we can write here this is minus V upon f delta f upon f, and this quantity V upon f is nothing but lambda. So, we can write here delta lambda upon lambda is equal to minus delta f upon f. So, let us say if I consider, just for sake of argument, if I consider a wavelength of 1000 nanometer, and if I take a spectral width, as we saw in our earlier discussion, a typical window size will be of the order of, let us say, 100 nanometer. So, if I consider this is 100 nanometer divided by, let us say, 1000 nanometer. you will get this quantity typically of the order of 0.1, which will be minus delta f upon f. Also from here, if I calculate what is the frequency typically corresponding to 1000 nanometer of wavelength, you will get a frequency f which is equal to 3 into 10 to the power 8 meters. Let us say we are working in vacuum, divided by the wavelength which is 1000 nanometer. So, which is 1000 into 10 to the power minus 9. So, this gives you frequency which is, this will be 9, 8, 17. So, this will be get about 3 into 10 to the power 14 hertz. So, at a 1000 nanometer wavelength would correspond to a center frequency of 3 into 10 to the power 14 hertz typically. And if I substitute that here, I will get now a quantity delta f, which is 0.1 of this. So, which will be equal to 3 into 10 to the power 13 hertz. So, since when we talk about communication, we normally talk the bandwidth of a system in terms of hertz. If you look at the number corresponding to the optical window, we have a bandwidth as large as about 3 into 10 to the power 13 hertz available in each window. So, this is a very small exercise which gives you a feel of what kind of large bandwidth we are talking about. When we talk about radio systems, the large bandwidth means few hundred megahertz, maybe gigahertz, maybe few gigahertz. But when we talk about large bandwidth in optical communication system, the large bandwidth means few terahertz. 1 terahertz is 1 into 10 to the power 12. So, we are talking here a bandwidth of something like 30 terahertz. So, an optical system is really extremely wideband system compared to the conventional communication systems. With this basic now preliminary understanding of light, now we can go to the basic structure which can guide light over very long distances. And this structure is what is called an optical fiber. So, optical fiber basically is a solid glass rod through which the light propagates, and this solid glass rod is surrounded by a shell again made of glass, what is called cladding. So, a basic structure which can guide light is a combination of core and cladding as shown here. So, you have a solid glass rod here which is core, and you have a shell which is surrounding it which is called cladding. The size of this total thing, core and cladding together, is of the order of about 125 microns. So, it is an extremely thin rod we are talking about. To protect this mechanically, then there are another layers which are present, what I call the buffering layers, and then some jacketing layers and so on, which do not have any role to play as far as light propagation is concerned. They are just for the mechanical support. But the basic structure which is needed for guiding light effectively is the combination of core and cladding. And the light essentially propagates inside the structure by a phenomena what is called the total internal reflection. So, if the light is sent inside the core, and if the refractive index of core is larger compared to the refractive index of cladding, then we get a phenomena what is called total internal reflection. And then by multiple total internal reflection, essentially the light propagates inside this core over very long distances. So, to start with, now what we can do is, we can take the simplest model of light, that is the ray model, and we can say that if the ray is launched inside this core, and if these conditions are made such that the light can be totally internally reflected at the boundary of core and cladding, at the interface between core and cladding, then through multiple total internal reflection the light can be guided. That is what precisely we will investigate when we meet next, that we will take the structure, the core and cladding structure, first discuss very briefly about the basic laws of reflection and refraction. We also discuss about what is total internal reflection, and then we discuss the issues related to the propagation of light inside this core by multiple total internal reflection.